So welcome everybody. LISP brings some very good memories for me back from 30 years ago. So I'm very pleased with Christopher from Sweden to talk about it. Thank you.
Thank you. Yeah, so I'm going to go back even further, like 60 years ago. Maybe even further than that. We'll see. My name is Christopher. I'm from Sweden. I work from home. I have 4 cats. This is my 3rd visit to LinuxConf AU, and I really love it. So really glad to be here. So you may know me from talks such as Package Matters All the Way Down. So I was really happy when I saw that Jonathan Corbett wrote an article about that talk. And also, Everyone Gets a Pony. Oh wait, no, this is not the right one. This is mine one. Yeah, so anyway. And also I work for SUSE, and they are the ones who were gracious enough to send me here, so thank you to them. But of course, they're not responsible for anything that I'm going to say in this talk. It's all my own insanity, so don't blame them. So I don't know if you've heard of this project called Papers We Love. And that was kind of how this presentation started. I read this paper by John McCarthy, who is the author of LISP. And yeah, when I put in the talk, I put like it's 1959, but now I see that it's actually 1960 on that talk. So he did the work in 1959, let's say that. But yeah, so this is going to be more of a historical deep dive based on this paper, but not just restricted to that paper, and not really that much about LISP itself. So if you're hoping to see tons of parentheses, there's going to be some, but not so many maybe. So I've kind of, one of the things that I did after I read this paper was that I decided I wanted to write my own little LISP interpreter. And I think that's something that everyone who looks at LISP gets into, and there's good reasons for it. And I've written maybe like 4 or 5 since then, and so that's part of the fun. So we're going to go back a little bit more right now. We're going to start somewhere in the period of 1955 to 1958. And around that time, 2 professors at MIT decided to break out of mathematics and start a new lab. Marvin Minsky and John McCarthy, and they created the MIT AI lab. And AI stood for artificial intelligence, and this was a term coined by John McCarthy to basically investigate how to make computers think like human beings. And their background was in math and in logic. So John McCarthy was an interesting guy. This is a picture from 1967 when he's playing a game of computer chess against a Soviet team with a computer program playing chess of their own. And the Soviets won by 3-1. Maybe that's why we haven't heard it so much about this in the English-speaking world. And his parents were both communists, and he grew up speaking Russian. And actually, he got his passion for math and for logic from reading Russian language books that he got from his parents. So I just thought that's kind of an interesting part of it, because most of this story is during the Cold War, and a lot of the stuff that was done in the relationship with the military as part of that. So, but yeah, the thing that he was trying to do was to make computers think, and the feeling that they had at that time in 1955 and 1958 was that this is just around the corner. We're right on the cusp of having computers that think like human beings. All we need to do is figure out these small things, like how do we represent knowledge in a computer, and how do we get the computer to, reason and logic and use logic like a human being? Because remember, these are mathematicians and logicians, so they were thinking, oh, humans, we use logic when we think. So this is kind of like what we're thinking. So they were very focused on that. So this is the title of a paper that John McCarthy wrote a few years later. There was a talk about AI this morning from Martin, I think his name is. Yeah, so that was really good. So I recommend seeing that if you haven't. But yeah. AI turned out to be really difficult. It's kind of fun to see, I mean, interesting to see, now that I've been reading all these old papers and kind of the attitudes and the ideas that they had then, to see the image of AI that's coming back now with AlphaGo and with self-driving cars and so on, where there's kind of been a renaissance in AI. Suddenly, oh, machine learning and deep learning and all this stuff, like, oh, it's possible. And it turns out, oh, maybe it's actually kind of difficult still. So we'll see. Maybe there'll be a second AI winter. I just had like 2 examples of articles. So this is one that's very positive. So there's from Sweden, where Volvo and Skanska have created a quarry that's using all self-driving autonomous quarry machines, and they've been able to reduce carbon emissions by 98% because it's all electric. So that's a really positive thing. And I think, yeah, this is a situation where self-driving cars definitely can work because this is a very controlled environment. On the other hand, there was this article a while ago from the CEO of Waymo. So Waymo is the self-driving car project from Google, and it's widely considered to be the best self-driving car project. Like they are the ones who've gotten the furthest. And yeah, he's kind of trying to down the hype a bit. So maybe self-driving cars aren't quite there yet. But anyway, in 1955, AI was just around the corner. So moving forward to 1956, we're starting to get into the history of programming languages. So up until this point, all programming languages were assembly languages. And this is also an assembly-based language, but it's the first list processing language. And so this is one that McCarthy himself cited as a big influence on LISP, because he saw what you could do with IPL in list processing, and he was thinking, this is how I can represent knowledge for for computers, is by having these lists that represent sentences of knowledge, and a list can contain another list, and then you can build trees, and now you can build up a whole tree of knowledge, and this is how you can represent programs for computers to work on. Then the second one that came out in 1957 was Fortran. So Fortran was really like the first high-level language. It's the first algebraic language, like a language written for humans to write and read, that's then compiled into machine language and machine code for the computer to read. So that was the other big influence that kind of made this click for him. So in 1958, McCarthy started the project to create LISP. So this is kind of the time frame. And the cool thing to me is that how quickly this all happened. So this is just in a matter of a few years. They created a lab, and then all these things started falling together. So already in 1958, his writing was going to become LISP. So we move forward 1 year, and we get to 1959. So the MIT AI lab got a computer donated to them to work on. So computers these days were not that easy to get, but they managed to get an IBM 704. And the IBM 704 had a really big influence on LISP later, as we're going to see, in maybe ways that you kind of wish you could get away from, but at the same time, it's there. So that's how it is. I have this really great quote that I want to read to you about the IBM 704. It's basically, the computer basically consisted of 3 fridges, or like huge boxes. One was the punch card reader, so that's where you fed in the punch cards that the computer program was on. So you had these little paper cards that had holes punched out of them, and then you fed that into a reader, and that in turn fed the program into the processor. So the processor was another big fridge that had a bunch of blinking lights where you can see what's going on. That's the state of the computer. And then that in turn fed into another fridge, which was the printer. And if you were lucky and everything worked, you got a piece of paper out of the printer and it said something. So your program actually worked. And that's how the computers were in those days. So it may be hard to visualize a 704 or to comprehend the place it held in the public imagination as the type specimen of what a computer was. A collection of mysterious hulking gray cabinets, approachable only through the intercession of the operator. In the specially built computer room, the operator set switches, pushed buttons, and examined panels of flashing lights, while assistants attended various whirring, clanking, and shattering devices, rushing to and fro with stacks of cryptically printed paper, decks of weirdly punched cards, and reels of brown ribbon, all to the background hum of the machine. Add a little incense and a few candles, and you could be forgiven for thinking these were the rites of some oracle shrine. So that's computing in the early days. And so I have this video that I'm not going to play to you. So I have the link in the talk. You can find it later if you want. It's about a half hour long. This is not a 704, but this is an IBM 1401, which is a later model. But this one is still running. So this is a video from just maybe a year ago, when they actually ran Fortran and compiled a Fortran program on it and got it to run and produce output. So that's pretty cool to see it's actually working. And yeah, there's some interesting points where they feed in the cart and suddenly stops eating carts, and they have to go and look at the lights and figure out, okay, what happened? But now I want to take a step back in time even more, because once I started looking at these old computers, I got really fascinated about old computers. And I want to see like how did that all happen? And I found this track of investigation. I think you're going to see the theme that I wanted to go down. So I found this program called the ENIAC Programmers. And the ENIAC Programmers was a project that was started in the 90s to investigate who were the first programmers of the ENIAC machines. And these are two of them. So one thing to know about the ENIAC machine was that it was built to calculate missile trajectories for missiles fired in war to see where they were going to land. And in the Second World War, this was all done by human computers. So they didn't have computers yet, but they had human computers, which were rooms filled with women, basically, who were doing all these calculations by hand. So it took days to calculate these missile trajectories by hand. So when they actually built the ENIAC, they needed people to actually program the ENIAC to set all the switches and all the cabling so that it would do what they wanted to do. And so they took, or they recruited, I think a team of 6 women from these human computers during the war. And so they were led by Jean Jennings Bartik. She was the head of the team. And there were 6 other women were part of the team to program the ENIAC. So these are the first programmers, you could say. So the other person in the photo is Fran Biles. And there's a quote that I found about that. Because they were women, it was assumed that the work they did must not have been very difficult. So no one really thought about programming then, because, done by women, obviously not important. Everyone focused on the machine. But now in the 90s and forward, we actually dug up and they actually found some of these women and interviewed them, and there's a whole video about them, and it's all really, really cool. So you can go and see that, and that's at eniacprogrammers.org. You can find more information about them. And I also found that in Sweden, we have a similar history. So the first computer that was built in Sweden was called Bark. And the Bark computer was programmed by this woman. She's called Elsa Karin Bostad Nilsson. And also someone who's not very well known, and not well known in Sweden, but they've actually done some interviews with her now, and she's still alive and still full of energy and an interesting person. So yes, kind of fascinating that this is something that when I went to school in Sweden, I never heard about for sure. But it's cool that this history has been discovered. So yeah, now I went down this rabbit hole, so I started finding more interesting people. This is Vera Watson. Vera Watson was the wife of John McCarthy, and she was a programmer. She was also of Chinese-Russian descent, and she was hired by IBM for a machine translation project because she spoke Russian. But she turned out to be a really good programmer, so she stayed at IBM as a programmer. And she later worked on the IBM System R, which was the first SQL database. And I haven't been able to find out more about exactly what she did and so on, but it's interesting. It's an interesting story. And even more interesting is that on her spare time, she was a mountain climber. And she was a really accomplished mountain climber. So Vera Watson was the first woman to climb Aconcagua, which is the highest mountain in the southern and western hemispheres. And she did that in 1974. And in 1978, she was part of the American Women's Himalayan Expedition, which was a team of all women who went to Himalayas to climb Annapurna 1, which is one of the 8,000 meter high peaks in the Himalayas. I'm not sure how to say that. And unfortunately, as part of that effort to climb Annapurna 1, she and one other climber died. So they split the team into two, and one team managed to make it to the peak, and the other team, unfortunately, got lost and died. And when you see the, when you see the mountain that they were climbing, you can see that this is not a trivial climb. So one more of these. When I looked at the first manual for LISP, which was published in March 1st, 1960, there's a list of names who were, or these are the people who were involved in making the first version of LISP. So these are the people who were part of the MIT AI lab in 1960 working on LISP. And on that list, we have John McCarthy, so he's the professor running the lab. Then we have a bunch of graduate students, not that important, they're all students. And then we have P. Fox, so that's Dr. Phyllis Fox. And I couldn't really find much information about her, so that's nice, had to investigate. So Phyllis Fox was a human computer during the war. And she was actually on one of the teams with Gene Jennings from the ENIAC. She worked on the UNIVAC together with Gene Jennings, which was a later computer. She then went on to write a language called the Dynamo language, which was the first simulation language. And this language was kind of interesting because it was used to do a quite famous simulation in the 70s in the US called Limits to Growth, where they tried to simulate all the world's resources and all the world's economic activity forward in time and see what's going to happen. Are we going to run out of things? Are we going to run out of space? What's going to happen? And they came up with three scenarios, or the simulation came out with three scenarios. Two of the scenarios saw an overshoot and collapse of the global system by the mid to late part of the 21st century. So it's coming up. While a third scenario resulted in a stabilized world. So we're not doomed. We have a 1 in 3 chance that things are going to work out. And then after she did that, she moved into the MIT AI lab. So thinking about that, they have a team of John McCarthy, who's never written a programming language before, but he's interested and he wants to do one. They have a bunch of students who obviously haven't got much experience. They probably haven't seen a computer before they came to the lab. And then we have Phyllis Fox, who actually wrote a programming language before, has experience as a human computer, and has worked on a computer before. And if we look at who's credited with what in the manual, everyone is credited with working on some part on the system except her. She is credited on writing the manual. That's it. So I thought that I don't have any proof that there is anything fishy going on, but clearly there's something fishy going on. After she was at MIT, she moved to Bell Labs, the birthplace of Unix. And there she worked on a math library called Port, and she wrote a high-efficiency matrix package, HEMP. I thought that was a little bit funny. Anyway, I don't know anything about those, but yeah. Back to Lisp. So representing list structures, representing sentences by list structures seemed appropriate. It still is. And the list processing language also seemed appropriate for programming the operations involved in deduction, and still is. So just so you know, Lisp was invented in 1959, 1960. It's still right. You know, if you're doing it in another way, you're doing it wrong. And yeah, so famously there's this, meme, and I've been wondering why this meme exists, and now I know, because I actually read the stuff he wrote. He was an opinionated man, let's just put it that way. Yeah, so why was he coming up with Lisp? He actually thought that the Turing machine was way too complicated. What he wanted to do was find some way to represent computation so that a computer can work with it. And he wanted a mathematical notation for working with programs. And using the Turing machine as your basis for your mathematical notation makes things very complicated, because the Turing machine is a complicated mechanical thing. It's, it's a reel of tape, and it's an infinite reel of tape going through a machine. It's really not really very clean, very mathematical. So he came up with the Lisp notation, and he wanted to show that actually this Lisp notation can be used to represent computation in a much better way. And he thought the way to do that would be to write the universal Lisp function. And by the universal Lisp function, he meant a function that takes a Lisp program as its argument and then executes that function. So that's what he did. He simply wrote that down. He thought, that would be a good idea. Let's do that. So yeah, he came up with what he called the eval function. So this was the Lisp function eval, which computes the value of a Lisp expression. Writing eval required inventing a notation representing Lisp functions as Lisp data. And such a notation was devised for the purpose of the paper, with no thought that it would use to express Lisp programs in practice. So the Lisp programming language actually was never intended to be a programming language. It was just a mathematical notation that we could use to write down programs. And it was mainly meant to represent Lisp functions as Lisp data. So yeah, we'll get to all that. But what happened was one of the students on the paper I showed you before, a guy called Steve Russell, he saw this eval function, and his job in the lab as a graduate student was to hand compile pieces of code to machine code. So he was spending all his day just hand transcribing code into machine code. It's very boring. So when he saw this function, he thought, well, I can just do this one, and then I can just feed my programs into this eval function, and it will take care of the rest. My job is done. And so this is a quote from John McCarthy. So Steve Russell said, look, why don't I program this eval? And I said to him, ho, you're confusing theory with practice. This eval is intended for reading, not for computing. But he did it anyway. You can kind of see that he's a fun-loving guy. He's not gonna. So actually, Steve Russell is famous for writing the first computer game called Space War. So that's what he's doing here. He's playing his own game later. So it's also a fascinating character. But yeah, we have eval. So at this point, I should probably introduce kind of the Lisp syntax if there's anyone who hasn't seen it before. So the Lisp syntax is based on something, the inspiration for it comes from something called the lambda calculus, which was invented in the 30s by Alonzo Church. And if you look at the Turing machine and the theories of computing by Turing, they usually placed side by side. So these were, Turing was coming up with his ideas, and Church was coming up with his ideas, and they were kind of independent. But in retrospect, they both kind of represent the same concept. So you can represent computing with this basic notation. The idea is that all computations can be expressed as function application. So you break any kind of computation down into the creating of functions and the calling and application of functions. And the result is a syntax that has a lot of parentheses. And it's clear that this was an issue already from the beginning. So this is a quote from the first real Lisp manual, the first one that was released kind of to the public. And it says, to prevent reading from continuing indefinitely, each packet should end with stop, followed by a large number of right parentheses. And each packet in this doesn't mean network packet, it means each packet of punch cards. So as you were feeding punch cards into the machine, you would put in an extra card that used to have a bunch of right parentheses so the computer wouldn't just go on forever. So yeah, these days, if you have an editor, you want to have an editor that highlights your parentheses, and it helps a lot. You don't want to sit there and write by hand. So these are the basic of Lisp, it's actually really, really simple if you break it down to the basics. So you have two kinds of things. You have atoms, which are symbols like foo, and you have lists, which are lists of atoms or lists. So in this case, we have foo, which is an atom. We have A, B, C, D, which is a list of 4 elements. All the elements are atoms. And then we have an empty list. So a list is represented by parentheses and end parentheses. And this is represented in the traditional Lisp implementations as a series of cells. So my beautiful drawing here shows the value foo, the atom, as kind of a blob on the side there. And then you have a series of 4 cons cells, and each cons cell has 2 parts. And the first part is what's in that cell in the list, and the next part points to the next element in the list. So it's like a train of cells. And this is how the list is usually represented in memory. So if we go to a little more complicated example, this is a list of 2 lists, and each list contains 3 symbols. And the drawing shows kind of one train with 2 elements. And in the first train, we have another train of 3 elements. And in the second train, we have, and in the second cart, we have another train of 3 elements. Oh, well, this gets really hairy. Once you're actually like poking around with this in memory, it gets confusing. But that's how it is. And yeah, some of the choices don't help. I'll get to that. Function application is represented by a list. So the first element of the list is the function that we want to apply, and the rest are the arguments to the function. So here we call the function f with the argument x. Then in some lists, truth and false, truthness and falseness is represented by either anything or the empty list. So anything is true except the empty list, which is false. Whereas in scheme, which is one of the dialects of Lisp that is still used, you have dedicated symbols for truth and false. So any functions that return true or false return dedicated symbols. So these are like different flavors of Lisp that you'll see, I guess. The next concept that I want to show you is quote. So one problem you run into when you want to deal with lists and functions is that if you're representing function application as a list, how do you deal with just lists? You don't want to apply this as a function. You just want to talk about it as a list. And the way you do that is by quoting. So you have this primitive operation, which is quoting, which just returns whatever you pass to it without evaluating it as a function. So if you give the symbol A to quote, it just returns A. If you give the list ABC to quote, it just returns list ABC. If you just wrote ABC, the compiler would think that this is, or the interpreter would think this is a function application, and would try to call the function A with B and C as arguments. So that wouldn't work. And in most implementations, quote is simplified as putting a little quote at the beginning of the list. So you would usually see this notation where you have a little quote there, and then it goes ABC, and that's what that means. Now we come to the influence of the IBM 704. So some other of the primitive operations that you have are for manipulating lists. And the first one you have is cons, which stands for construct. So you're constructing a list or a list cell. And that takes 2 arguments. It takes the thing that you want to add to the list, and then it takes the list. And you add to the front, because what you're doing is you're adding a new cart to the front of the list. So basically you're getting a new list. And then you have the operations car and kudr. And car is short for the contents of the address part of the register. And kudr is short for contents of the decrement part of the register. And these are artifacts from the IBM 704. So the IBM 704 had 36-bit registers. And the registers were divided into a series of parts. I think it's 5 parts. And 2 of those parts were the address and the decrement parts. So you had a tag, you had an address, and the decrement. These are concepts that still survive in most Lisps today, even though the IBM 704 is long gone. And the main reason for that is that there's a thing you can do with car and coulter where you can put a series of calls to car and coulter together into kind of a new function name where you just mix A and D. So you put C, A, D, and that means, oh, now we call car, and then coulter, which gets quite convenient when you want to poke around in big list structures, which is difficult to replicate if you change it to first or next. Yes. Yes, you're right. Yes. Yeah. So coulter returns the rest of the list. So yeah, that's a bit of a mistake. Yeah. So to clarify. Right. So it depends on what y is there, but yeah, it wouldn't return y. Yeah, so don't look too closely on that. But yeah, let's just move on. That got a bit confusing. But basically, coulter returns the rest of the list, we can say, because the second pointer in the console points to the rest of the list. Right. Yeah. Then we have a syntax for creating functions. So this is called lambda, and again, this is kind of an historical artifact. It comes from the lambda calculus. You could call it function. That would be too easy. But this is generally how it's done. There are some Lisps these days that don't. They use like fn or a fun or function or something like that for the same purpose. But in this case, we can see another kind of thing with using this syntax is that there's no special syntax for mathematical operations. There are no infix operations. Everything is a function. Everything is function application, including multiplication. So you have this Polish notation. I'm not sure exactly how you call that, where multiplication, reverse Polish notation. Yeah, they had a word for it. Yeah. Where, yeah, we're multiplying x by 2, and we do that by calling the function multiply or star and passing it x and 2. The benefit of that is that you can easily pass more than 2 arguments to anything, including mathematical operations. So the syntax gets a lot more unified. But actually writing math like that is a little bit painful. So that's the price you pay. And then when you create a function, you can actually just call it directly. So here we're creating a function that multiplies by 2, and then we're passing in 4. So this should return 8, if we're lucky. The next thing that is in kind of this basic Lisp is the conditional operation. And it's actually kind of interesting is even though Fortran was invented the year before, conditionals hadn't been invented yet because everyone was still thinking in machine language. So what Fortran had in the first version was just operations to jump to another location in the code if a certain value was 0 or not 0. So you had these like branching operations where you can say, okay, go to line 5 or whatever, but you didn't have if or else. That hadn't been invented yet. So that was one of the big innovations in Lisp, is that you actually had this conditional expression. And the way it works is that it takes a series of lists of 2 elements. And it evaluates the first element in each list. And if that's true, it evaluates the second element of the list and finishes. If it's not true, then it goes on to the next pair in the list. So you get this series of if this, then do this, else this, do this, and so on. So it's basically a series of if statements. And that's the basic conditional operation, not if and else. So this came first. We then have checking for equality. In the basic Lisp, there's 1 equals. Once you start working with these kind of languages, you realize you need a bunch of different kinds of equality. You need, are they actually the same, or are they of the same structure? Like if you have 2 lists that look the same, are they the same? So on. So in modern Lisps, you usually have a bunch of equality operations. In the basic one, they just check directly if it's exactly the same thing in memory. And then we have something that in the original version is called label, but which in Scheme is called define. So I changed it to define in my little implementation, just to be clear. And that's just giving a name to a function. So you would pass it a function, and then now you've named your function so you can call the function by name. And really, this is the whole language. This is all you need. So now we can do, for example, faculty operations. There are some, of course, you need to implement like basic math operations if you want to do math. You actually don't have to. So in the lambda calculus, you can do math and numbers as structures of function applications, but that becomes very difficult to work with. So this is pretty impressive that this is really all you need. This is the whole language. And given this is what John McCarthy wrote. So this is the eval function. And one thing you probably notice is that this doesn't look like what I showed you at all. This is some kind of weird brackety syntax with the functions getting their arguments in a like square bracket thing. And that's because, as I said, John McCarthy never thought that S expressions was the way to write the language. He was working on a different language called M expressions. That was going to be, the programming language. That was going to be Lisp. It's just that no one ever got around to actually implementing that. So this is only found in these early papers. But this is the basic eval function as it was written in the Lisp 1.5 manual. And I have a quote from Alan Kay. And Alan Kay was the inventor of Smalltalk and the first, or one of the people who invented object-oriented programming. And he has this quote that I've seen in a bunch of places, but it's quite good. He said that, yes, this was the big revelation to me when I was in graduate school, when I finally understood that the half page of code on the bottom of page 13 on the Lisp manual, Lisp 1.5 manual, was Lisp in itself. These were Maxwell's equations of software. This is the whole world of programming in a few lines that I can put my hand over. So this is page 13. So that's that. And it is kind of mind-boggling that this is really all you need to implement the whole language. And also that this is Lisp defined in terms of Lisp itself. So I guess that's the kind of the next interesting thing that he came up with, is that there is really no difference between code and data. Code and data are really just the same thing. There is no sharp boundary between what's a data format and what's a code format. And that's something that was realized as early as 1960. But I think it's something that we still kind of struggle with, grasping. And it's one of the reasons why I think there's some of the vulnerabilities and security issues that we have, because we don't realize that actually passing data to a program is passing code to a program. And it's one of the things that I think Lisp is really good at, is manipulating code as data. So one of the things I'm not so fond of is XML. XML is okay for data, but it's terrible for code. And invariably, when you do a big project and you have a big configuration file and so on, you're going to have some bits that are more codey than data, and they're going to look awful in XML. So in Pacemaker, which is a project I work on a lot, we have rule expressions, and yeah, they are horrible because they're code written in XML. So this is where I wish we saw more Lisp, maybe. So what's happened since 1960? So there are a bunch of languages based on Lisp around still today. So there's Scheme, Common Lisp, Emacs Lisp, Closure, ClojureScript. But I think Lisp in itself is not really that interesting as a language, to be honest. And clearly John McCarthy agrees with me, so I'm not completely wrong about that. There are some uses. So there is GNU GUIX, which is a functionally based package manager and operating system. So that's kind of interesting. And that's using Guile, which is a scheme implementation. But most people don't work in Lisp these days. But a lot of the ideas that started in Lisp are still around. So the interpreter, for example, is something that we're all used to today, to be able to interpret code instead of having to compile it. But that was a big innovation. Garbage collection was an innovation from Lisp, and that's something that we see everywhere today. A lot of the people that were involved in Lisp were also involved in Java later on, so there's a big overlap between Scheme and Java. even if the syntax and the language are very different. The basic virtual machine and garbage collection and so on, those ideas resonate. JavaScript, Perl, Ruby, Python, these are all kind of LISPs. They just don't have the parenthesized syntax, because even though people who are really into Lisp like to say that, you know, the parens, you get used to them and they're actually awesome and code is data and you can pass code to functions and all that's great. That's true, but for most people, it's not true. It's actually, you know, too many parentheses. And that's just how it is. So why am I talking about Lisp? And that's kind of a question that I've been asking myself, like why am I so into Lisp? And it actually led me down to a different path of thinking about programming languages. And it's made me think, why do I find Linux so interesting? And why open source and free software? And why am I so into like the ideology of software and this whole like open source, collaboration, all that stuff? And I think the reason why I'm into Lisp and why I'm into open source is kind of the same. And it's about culture and it's about a connection to the past. So I really like history and I really like that. And I think there are kind of, you can look at things in two ways. So you can value innovation and intelligence and entrepreneurial spirit as the highest ideals, and that's the most important thing. Or you can value wisdom and craft and working on something to imperfect it and building on the things that other people have built before you. And when you think about that, if you think about wisdom and you think about craft, then sharing becomes natural because you want to share, you want to learn from others, you want to give back to others, you want to teach others how to do something just right. And I think that's kind of the overlap and the connection back to Lisp, because with open source, with free software, we're working on and building on this legacy that's coming from all the way back to the first computers and the first programmers. And if you're talking about proprietary software, really what you're doing is you're making a break in history. You're taking that chain of legacy and history and sharing, and you're taking and breaking off to your own part, and you're not giving back. You're being antisocial. And I don't like that. I don't like that at all. So there was a talk earlier in the week talking about the importance of teaching assembly language to new programmers and students and young people so that they can really understand how computers work. And I think actually, even though when I was in university and I first had to do Lisp stuff for AI, I didn't like it at all, I didn't get it. I actually think it's really important as well, because Lisp tells you the fundamentals about computing. It tells you what are programs actually, not like what does the machine do, but what is computing? If you can look at the eval function, you have the whole concept of programming in a screen of code. You can actually understand that, okay, so this is how a program works. So I think that's really important. And so the thing I want to say about that is that I actually don't think that, one way of thinking about free software is that it was a new idea that Richard Stallman came up with. And in one way it was. But actually it wasn't a new idea at all. It was trying to defend the old idea, the old concept of actually sharing and building on the knowledge of others and not taking things and moving them off and not sharing anymore. So for me, free software and open source is not a new invention or a sidetrack or something weird. It's actually the unbroken lineage that goes back to the first Lisp interpreter and continues in Linux today of a culture building on itself. And it's proprietary software that breaks that. And so that's what I think. And I don't know if I have time. Now I had 2 minutes, so maybe I can mention this. But I have cultural reasons for thinking this way as well. So I come from the north of Sweden. And I don't know if you've heard of the Sammy people. Okay, so I get some nods. So the Sammy people lives in northern Sweden, Norway, Finland, and Russia. is the last remaining indigenous people of Europe. It's a nomadic people. They lived in the north of these countries for thousands of years with a culture that was unbroken. They were living peacefully and sustainably in the nature in a very extremely and hostile climate. And they had practices that carried back all the way in order to be able to survive in that harsh environment. And what happened was, oh yeah, so this is the weather on Tuesday in my hometown. It's pretty much exactly the opposite of here, so I'm pretty happy to be here. So what happened was that in the 17th century, Sweden was beginning to be an imperial power in the world. And the imperial powers of Europe were starting to spread all over the planet, and of course Sweden wanted to be part of that. But they weren't very successful. But at the same time, they discovered silver in Sweden, in the north of Sweden. So they decided, we can do our imperial colonial thing in Sweden instead of going to other places. And they started to defining the borders of Sweden up. And so what they did was, I have a specific example from my own history. It's one of my ancestors, a man called Adam, the son of Christopher. And of course, we don't know the name he was given by his parents, and we only know the name he was given by the priests who took him from his parents against their will and took him to school in southern Sweden and brought him up and cut his link to the past. And of course, he could now no longer continue the lifestyle of his parents. And so they gave him a piece of land in Vilhelmina, and he became a settler. And that's how they settled the north of Sweden. And so it's fascinating to come to Australia and to New Zealand and see the culture and the history that's going on here, and knowing that the same thing happened in Sweden in the 17th century. And this is a drum that's a Sammy artifact that I have. This is a modern reproduction. We actually don't know anything about what these symbols mean because all that knowledge has been lost. And there were only 70 drums that survived the 17th century. Because they were taken and owned by noble families and so on. But probably this was something like a cultural and geological map showing how to find things and so on. But yeah, all that's gone. And so yeah, for me it really matters having this link to the past and free software. So that's why. So yeah, I didn't get to my great finale.